Hi everyone, what's up? So today I want to go over integral uniqueness up to a constant. So I'm pretty sure you've heard in your calculus course that some antiderivatives have different answers that differ by a constant, okay? So today I want to emphasize that idea by solving this antiderivative here and showing you how the two solutions to this antiderivative. I'm pretty sure there might be more than two solutions, but the two most important solutions to this antiderivative, I want to show you how they differ by constant, okay? And well, we're going to use a trigonometric identity to show that, okay? So it's good if you remember some things back from pre-calculus, okay? So yeah, let's begin. So this integral, it's pretty easy to solve. You can just simply, you can choose a u-substitution. You can actually choose two u values to substitute. So the first one is going to be u is equal to sine x. I think that's the most obvious one since you have cosine x dx. And well, you can just simply, the differential of u is going to be cosine x dx, which is the rest of the integrand. And that means that, well, you can rewrite this antiderivative as sine x, that's going to be u, times cosine x dx, well, we know that it's going to be du, okay? So we have du here, and we know this would be u squared divided by 2 plus c, okay? And we know this would be equal to u equals sine, so this is going to be sine squared of x divided by 2 plus c, okay? So this is one of the solutions to this integral. And the other solution is going to be, you can let u be equal to cosine. I'm going to say that this is the first one, and this is the second one. So you can let u be equal to cosine x, and that would give you that the differential of u is going to be minus sine x dx. And now what can you do here? Well, you can see that, what should I do? I'm going to say that, I'm going to erase this one, so that, well, no, actually you should leave that one, I'm trying to optimize the space here, okay, because I want things to look good, but let me write this again. This is going to be sine squared divided by 2 plus c, and I'm just going to continue here, okay, this equals sine corresponds to this antiderivative here. So this antiderivative is going to be equal to, you have the antiderivative of cosine, that's going to be u, times sine x dx. So we know from this equation up here that sine x dx is going to be equal to minus the differential of u, okay, you can just move this negative one to the other side of the equation. And we're going to get that, well, this is going to be u du and a minus sign in front, okay? Because you have minus du here, so you can just simply plug du and move the negative to the front. And this is just going to be minus, I'm going to write, oh, sorry, this should be x, sorry. I'm just going to plug in the value for u, so this is going to be minus cosine squared divided by 2 plus c, okay? So these are the two solutions that you get for this antiderivative, or at least the most common ones. I'm pretty sure there might be, some other combination of trigonometric functions that yields this derivative. There probably is, but I'm not going to focus on that in this video. I want to focus on what happens with these two solutions. So I'm going to define, I'm going to let this solution be a function. I'm going to say this is going to be a of x, and this is going to be b of x, okay? Just so that we have names for those two. So now the something that you want to do now is, since we're trying to see how the solutions to an antiderivative differ by constants, well, one of the ways in math in which you can see how a quantity differs in 2 points, or two versions of that quantity, how much do they differ? Well, you can subtract those two quantities that you have. So how can we see the difference between these two solutions? We can subtract a from b, okay, or well, however you want to see it, the negative signs would work out, okay? So I want to do the following. I'm going to say that a of x minus b of x, the two solutions that we have, are going to be equal to, so you're going to see now a resemblance with a very common trigonometric function. This is going to be sine squared x divided by 2. We have the constants plus c and plus c, but when we use a negative sign here, well, the two constants, they're gonna disappear, so I'm not gonna write them. And here we're gonna get minus cosine squared, so this is gonna be, I'm gonna write the entire thing, so it's gonna be minus cosine squared of x divided by 2, okay? And now this, you can write it like this, so this is gonna be sine squared of x divided by 2 plus cosine squared of x divided by 2. Now, I hope that you can see some resemblance with a Pythagorean identity back from pre-calculus. There is a trigonometric identity that allows us to relate how sine squared and cosine squared, well, you know, how they relate to each other, okay? So basically, yeah, I'm gonna write it. So this is gonna be, the identity that I'm talking about is sine squared of theta plus cosine squared of theta is equal to 1. You can see that if you divide both terms on this equation by 2, you also need to do it on the right hand side of the equation, so you would get this. You can see that based on this identity, well, the left hand side of the equation is exactly the same as the expression that you have in this equation. Okay, so if you want to find what's the difference or what is the constant that makes the solution A and the solution B differ, well, you can see that based on this identity, this equation, or well, this expression, you could rewrite it as 1 over 2, okay? Because you can see that, well, we can, this is pretty much the same identity, okay? You're just simply multiplying by 1 over 2 the entire identity, okay? So based on this identity, you know that the solutions A and B differ by 1 over 2, okay? So what I'm trying to show you here is that when you have two solutions to an antiderivative, usually if you're dealing with trigonometric identities, you really want to try to think about some identity back in your head that you remember all the way back from pre-calculus. You want to think about those identities and try to see if you can match the form that you have of the difference of the solutions. So here we have the difference of the solutions, and the form, the expression, the result that we got is this expression. If you can match this expression with some trigonometric identity that you remember, well, you can find the constant that two solutions for an antiderivative differ by, okay? Differ by, is that correct? I think that's correct, yeah. So yeah, that would be the entire thing. This is, a pretty cool concept. I think it shows you how math is very well connected, a trigonometric identity is still consistent when you anti-differentiate and you subtract solutions and all that. Everything's, pretty consistent. So yeah, that's been the entire video. I hope that you enjoyed it, and see you in the following one. Bye.